Good afternoon, guys, and welcome back. We will now be talking about the actual structure, the information in chapter 14 for chemical equilibrium. Like I said, I did the intro for this earlier. This is the actual material from that class. So let's go ahead and get started with that. I'm going to share my screen. We're going to pick up partway through the discussion the slides that we were going through before for chemical equilibrium. So the first thing we're going to talk about is the concept of equilibrium. So I want to ask you about a couple of scenarios. Consider a hot day in summer. You make iced tea. Being in the South, you add sugar to your iced tea to the point where there is solid sugar in the bottom of the glass. You sit outside on the porch and drink it, slowly. The next time you look down, the solid sugar is gone. What happened? And I know I'm getting lots of answers like, oh, it's dissolved. Oh, this happened. Oh, this happened. Lots of things. What actually happens is that when you make that tea at a specific temperature, there is a specific amount of sugar that can go into solution. The rest of it sits on the bottom. It won't go into solution. Now, as time goes on, the temperature of that iced tea goes up because you're sitting outside. And so the temperature has gone up. Now, as the temperature goes up, the sugar is able to dissolve more. And that's why it disappears. It's not that it suddenly decided to go into solution. That's not what happened. It's that you can get more of it into solution because we've changed the temperature. Okay. So we've talked about that. So you're getting ready to make rock candy. You dissolve sugar in hot water. You then let the pan cool down very slowly without touching it. You put a stick in the water. Almost immediately, you find clumps of sugar on the stick. What happened? Well, I had water at a very specific temperature, and I dissolved a bunch of sugar in it. Then the temperature changes. It goes from what it was, this high temperature, to a lower temperature. What happens at that higher temperature is that you dissolve as much sugar as you possibly can, and that solution becomes saturated. So it has as much sugar in it as it can possibly have. As the temperature comes down, the amount of sugar that should be able to be in that solution is lower. Okay, and so the solution becomes something called supersaturated. So we have more in it than we think we should be able to have. And what happens is as soon as it gets disturbed, that all crashes out of solution. And that's what happens when you poke it with a stick. You poke it with a stick and stuff comes out because it's not able to be in that solution at that temperature. So there's that. Now, I'm an insulin-dependent diabetic. I carry insulin with me all the time. Unfortunately, I'm not always so great about taking it out of the car, and I left it in my bag in summertime. I came back out of the store to find a solid in the liquid. What happened? What happened? Why is it that I get solid out of this liquid when it gets warmer? Well, this is a slightly different process. So what's happened is that molecule, the insulin itself, has become denatured. What denaturization means is that the structure of it has changed. So you've gone from one, set of conditions to a different physical structure. That physical structure is no longer soluble under those conditions. Now, if I put that in the fridge, what happens? Anything? And actually, the answer to that is nothing. So the solid does not go back into the liquid because it's now been denatured, it's been changed, and it can't go back into the liquid because of that. All right. So that is not what we would call an equilibrium process. That's a different kind of process. We've actually changed the chemistry on that molecule. All right. That process is also known as irreversible. So I can do it in one direction, but not in the other direction. So that's a problem that we have there. So equilibrium is a situation that we'll define in just a minute. And here's the other thing about reversible reaction, okay? Even though we label some reactions as non-reversible, like the one we just talked about, what that means is that they lie so far forward that it's very difficult for us to see any of the reactants that are left. Even though there may be a very, very small amount of them, and that's usually what happens, we can't detect it, okay? So that's why we define it as a non-reversible process, because I only have the products of that reaction available to me in the beaker, okay? So that's what we mean by reversibility. If it's reversible, I can go from product to reactant and reactant to product all the way back and forth, but not all of them are able to do that. Okay? So what does equilibrium mean? Well, equilibrium is a condition where at a particular set of conditions, pressure, temperature, all of that stuff, there's only so much of something that can be formed. Now, we can talk about that in terms of solubility, in terms of how much sugar can I get to go into that iced tea. The only way I can change that is by changing that temperature. But that ratio of something being in the solid phase to something being in the aqueous phase is a reaction. And depending on what the temperature is, that determines how much of that aqueous stuff we have compared to the solid stuff. All right? Reactions are defined by the ratio of the product to the reactant, okay? And under a certain set of conditions, that always comes to what we call an equilibrium. So there is a fixed amount of product to reactant. That ratio is always the same, all right? It doesn't matter how much of each one I have, that ratio becomes the same. And it happens in a fairly very rapid time. Right? Equilibrium means that even though there's no net change to the product or the reactant, that concentration, that reaction is still happening in both the forward and reverse direction. I just can't see that I'm getting things going into and out of solution, per se, at the same time. Okay? So the forward reaction equals the reverse reaction. Same rate. All right? That does not mean that you have the equal number of products and reactants. That's not what that means. All right? Now, that's different from reversibility. Not all reactions are reversible, but every reaction comes to an equilibrium, and it does so very quickly. Okay? So, again, that concept, even though there may be either entirely product and reactant, in which case the K is undefined and we don't talk about it. There always is equilibrium. And that equilibrium means that I have things moving forward and backward both at the same rate. And that means that I have no net change of product concentration or reactant concentration. Okay? Now, equilibrium can be reached from either direction. In this case, we're considering the reaction between NO2 to NO2 to make N2O4. Okay? So the way that we talk about this in the first 3 experiments, we start with none of our product and start with some of the NO2. And then we wait a little while and we measure the concentration at equilibrium of both the N2O4 and the NO2. So the product and the reactant. And if you look at the amounts that you have, so I started with a smaller amount here than here, and I end up with a smaller amount here than here, but the ratio of the two is the same, okay? And that's the ratio that we're going to be talking about for the rest of this class. That's the numerical representation of equilibrium. But it doesn't matter if I start with product or start with reactant, okay? So either way, I can start with my product. I can start with my reactant. In both cases, in all cases, I get to that same ratio, okay? So I always have a fixed amount of product compared to reactant once that equilibrium has established itself over the period of time that it does so, okay? So it doesn't matter where I start. I always end up with equilibrium in the same place, all right? And the only thing that can change the ratio of product to reactant in that particular equation is changing the temperature. Now, let's talk about what we actually mean by that Kc. What is this description of equilibrium? Well, Kc is an equilibrium constant. Now, it's a constant that implies that the ratio is fixed. It is a ratio because we're talking about the concentration of the products over the concentration of the reactants. Each of those things is raised to the stoichiometric coefficient of that material in the equation. So if you are considering the reaction between NaOH and HCl to form NaCl and H2O, we're going to look at our products, NaCl on the top, raised to the first power because it's a 1 stoichiometry, the H2O doesn't appear. We'll talk about why in just a few minutes. Over the concentration of the NaOH, raised to the first power because it's a 1, times the concentration of the HCl, again raised to the 1 power. Now, the H2O does not appear. There are a couple of things that don't appear in K reactions, and we'll talk about why on the next slide. But we don't put in liquids and pure solids, or solids. We don't; those don't go in there. We have the concentration of the products raised to their stoichiometric coefficients over the concentration of reactants raised to their stoichiometric coefficients. There are a couple of things that you can take from this. The ratio of product to reactant is a constant under given conditions. This is regardless of source of the component. So I can have product that forms from a single reactant. I can have a situation where I add reactant and product, okay? And it doesn't matter how those things get added. I always end up with the same ratio at equilibrium, okay? Only things in the aqueous and gaseous phase are going to be in this K, all right? And no matter what I put in the beaker, the reaction is related to the ratio of products versus reactant, okay? That's what it is. Here's another point. Stoichiometry matters. No matter how much you may hate it, it's part of everything that happens from here on out. So this reaction is written as NaOH plus HCl going to NaCl plus H2O. But there's no reason that this can't be 2 NaOH plus 2 HCl going to 2 NaCl plus 2 H2O, except that it would change the nature of this K. K would then be NaCl squared over NaOH squared times HCl squared. So this K expression always reflects the stoichiometry of the reaction as it is written, right? That equilibrium will not change under given conditions, i.e. the same temperature. But we have to pay attention to the stoichiometry. I mention this because you cannot report a K to me without telling me what reaction you're writing the K for. I need to see both. The other thing, no matter what you do, if you make sweet tea, only so much sugar is going to go into that tea. That's it. At a given temperature, I cannot change it. And as much as I might want that sugar to go more into that solution, it's not going to happen. All right? That is a fixed ratio that we have there. All right. So at equilibrium, the concentration of reactants and products no longer change. That ratio is fixed. While the reactions still occur in the forward and back direction, there's no net change in that concentration. The rate of the forward and reverse reactions are equal. We'll talk about rate again later, but I just wanted to mention at this point that the rate forward is the same as the rate back at equilibrium. So what can I learn from an equilibrium constant? I now have this K that tells me the ratio of the product to the reactant, right? What does that mean? Well, what if K is really, really big? What does that tell you? Mathematically, that tells me that I have more product than reactant. Okay, the products are favored, so the equilibrium is favored to the right. All right, that's what we talk about there. What if K is approximately 1? Then the product and the reactant are in roughly the same concentration, and therefore there's no predominant direction. Backwards and forwards are considered in the same way. So backwards and forwards are considered in the same way. Now, if Kc is really, really small, that means that I am reactant favored. I don't have a lot of product that forms from this. I have a lot of reactant from this, and I can't really get that to move. Okay, so the reaction is said to be favored in the left direction, so the reverse direction. We'll see this for things like weak acids. They have very low K values, and so that's going to determine how much of that can dissociate at equilibrium. Okay, so that's what the nature of the K value means. All right, now we've talked about what an equilibrium constant is and what its implications are depending on its size. We can do things with this. So a couple of things I want you to think about. We had 2 solutions. 5 minutes later, we measure the amount of each product present. Then we wait 15 more minutes and do the same again. The amount of product has increased. What does that tell you? What does that set of conditions tell you? Well, what it tells me is that I wasn't at equilibrium. Had I been at equilibrium, I would see no net change in the concentration. So I wasn't at equilibrium under those first conditions. We had two solutions together. 5 minutes later, we measured the amount of each product present. We then wait 15 more minutes and do the same again. But the amount of product has not changed. Here we're at equilibrium because no change has been observed. So even though more time has gone on, I haven't gotten any more product compared to the reactant. They still have that same ratio. Now, I said we'd talk about liquids and solids in Kc again. Here we are. So Kc is the concentration equilibrium constant. That's what the C is for. So that's all that means. Any solid that's dissolved in water, that does dissolve, is in equilibrium with the water. So the solid can go into the water and come back out of the water. The rate of doing so is fixed at equilibrium. Okay? But you always have the same ratio of stuff in solution compared to the stuff that's solid. The thing is, the amount of that solid is huge compared to how much is in solution. All right, that's always the case. And so since it's such a big number, there's no way for us to differentiate that from this equilibrium constant. So it becomes part of the K, and we don't include its concentration in that expression. All right. The same is going to be true for pure liquids, because I have so much of that liquid around that I'm not going to be able to differentiate that from the equilibrium constant. And so those two things will not appear in our K expressions. So we need to know the state of each material to know whether it needs to be included in that particular K. And of course, reactions can happen under multiple conditions. So I could do a reaction with, hydrochloric acid and ammonia gas, or hydrochloric acid and ammonia aqueous, so dissolved in water. And those are two different K expressions. Okay. Gases are different in almost all cases. So since gases vary so much depending on all the conditions around them, gases are always included in the K, as are those things that are in aqueous, so they're in solution. So solids and liquids are not part of K, aqueous components and gases are. So that's what we have there. All right. Heterogeneous equilibrium. Now, the concentration equilibrium constant only applies when everything is in the same phase. A homogeneous equilibrium. And it has to be, it's in a particular place, usually a solvent, but not necessarily water. So, crap, I have to consider phase? Yes, absolutely you do. It's important that you know what those phases are. It has implications for the energy that's involved in making this thing. How much heat it needs or gives off, how much randomness is in that system. There are lots of things that are going to depend on that phase. And so we need to have that included when we talk about that K. There are other K values besides Kc. So Kc, again, is a concentration equilibrium constant where we're in some medium, not necessarily water. Now, if I'm in water, I can call that a KEQ. So KAQ, which is aqueous. If I'm in the gas phase, if everything's in the gas phase, we can talk about KP, right? So we're talking about pressures there, not concentrations. Are all the same expression. They just have a different subscript to help us understand what we're looking at. Now, if I have things in more than one phase, which is unfortunately a thing we see often, then we have this thing called the KEQ, which is the equilibrium constant. And it doesn't have the same considerations as a pressure one would or a concentration one would. So it just means that I'm in multiple phases. So I'm in a heterogeneous equilibrium. Right? The pure liquids and pure solids still do not appear here. There are other things that we have to consider if we're in multiple phases. So things like temperature, atmosphere, all that stuff for gases, some of those things affect what we see in aqueous solution, all of that stuff. So there's more to pay attention to if I'm looking at a KEQ than there is if we're talking about a Kc. All right? That's the reason that we have differences in what we call it. And again, if you have questions, if there's questions on anything, notice I've given breaks to have you sit, think, ponder. Let me know. Contact me, phone call, email, whatever. Let me know what topic we're talking about, what your question is, and I'll see if I can help. Okay? Now, multiple equilibria. I don't know if you've seen much of this, but sometimes we have a reaction that occurs in 2 steps. If we talk about a diprotic acid, so it has 2 protons and it can donate. H2CO3 is an example, and we'll talk about that later. If I know the expression for the first loss of a proton, goes from H2CO3 to H plus HCO3 minus, and I know a K value for that. And then I talk about the HCO3 minus going to give me H plus CO3 2 minus, and I know a K for that. Then I can take and multiply those 2 Ks together to tell me what the value would be to go directly from H2CO3 to 2H plus CO3 2 minus. Okay, so that's the kind of thing that we're talking about here. I have a process where A plus B gives me C plus D. C plus D then turns around and gives me E plus F. The overall reaction is then A plus B going to E plus F, right? You understand that because the C's and D's have canceled since they're on opposite sides. The equilibrium expression for this first reaction is C times D over A times B. For this reaction, it's E times F over C times D. And for the overall reaction, it should be E times F over A times B. This right here. But I know that to get this, I can multiply these 2 things together and get that value. So that's where that's important. If I can see, based on the structure of the K, that I can get a value for something else other than what I've been presented by multiplying them together, then I can use those values for K that we will eventually get to get a number for that overall process. Right? So that's what this is showing. That will come into play a lot more later. Form of K and the equilibrium equation. All right, forward versus reverse reaction. So consider the reaction N2O4, okay, breaking down to give me 2NO2. The K for that is K equals NO2 squared over N2O4. However, if I turn it around and I go 2NO2 goes to N2O4, then that K is N2O4 over NO2 squared. Now, those are very similar expressions. Absolutely they are. They're the inverse of each other. So if I know the K for the forward reaction, and I want to know the value for the reverse reaction, all I have to do is take the inverse of it. Okay? And stoichiometry matters. I said this before. This equation that I'm looking at here is N2O4 goes to 2NO2 and gives me a K of NO2 squared over N2O4. If the reaction is instead written as 1/2 N2O4 goes to NO2, then the expression for K will be K equals NO2 over N2O4 to the 1/2. This K is not the same as this K. This one is the square of this one. So if I take the square root of this, I get this. So there is a relationship there, but you need to make sure that you're reporting the K expression for the right value, okay? Because these will have values, and you need to make sure that you're talking about the right one, okay? That's why stoichiometry is important. All right. We will talk about the relationship between kinetics and equilibrium. Now, kinetics is reaction rate. We haven't talked about this yet. This will come up in a few lectures. Regardless of how a reaction proceeds, no matter if it's a single step or multiple steps, the equilibrium expression for the reaction is always written as what we've talked about here. Products, the concentration of the products over the concentration of the reactants. This is because of what we talked about with the multiple equilibria. That's why this is true, okay? So it doesn't matter how that thing occurs or how fast it occurs or anything else. The equilibrium expression is always going to look the same. Now, we talked about what does the equilibrium constant tell us in terms of its size. So if K is large, we expect a lot of product. If K is about 1, we expect the same ratio of product to reactant. If K is very small, we expect a lot of reactant. But what if I change those conditions? What if I'm no longer at equilibrium? Or I haven't, I just mixed stuff together and I want to know, am I going to be at equilibrium? Or which direction is this equation going to go to get to equilibrium? We can then define something called Q, which is the reaction quotient. So this is structured exactly the same. Concentration of the products over the concentration of reactants raised to their stoichiometric coefficients. But this is not at equilibrium. That's the only difference. We use this to measure, are we at equilibrium yet? 1. And if we're not, how are we going to get to equilibrium? Do I need to go forward or back? So if K is equal to Q, if Q and K are the same, I'm at equilibrium, everything is good, we're all done. If Q is bigger than K, that means I have too much product compared to the equilibrium condition. If I have too much product, I favor the reverse reaction to give me more reactant. Okay, so that's how that works. Now, if Q is less than K, I'm in a situation where I don't have enough product. I have too much reactant, not enough product. So now I need to go forward to get more product and less reactant. So that's what that's going to be, all right? That allows us to calculate how, and of course, the other thing that the equilibrium constant can tell us is what are those equilibrium concentrations? So they're fixed based on that ratio. What are they? Okay. And the way that we talk about that is through something called an ICE table or a RICE table, depending on where you're looking, what you see. It's one or the other. And I'll explain why they both get used as expressions. So RICE tables, aka ICE table. In some textbooks, this is listed as the initial, these are my initial conditions, the change, what happens during the course of this reaction as it's written, and my equilibrium. So what is that concentration going to be at equilibrium? So if I start here with the H plus and I minus, and I have concentrations for both of those, then I'm going to take away some of the H2, take away some of the I2 to make 2HI. So that's where this equilibrium or the change comes from. The negative x, and the plus 2x, based on the stoichiometry of the equation. So 1 here, 2 here, that tells you how many x's. It's negative if we're taking away from what we have as it's written. It's positive if we're adding to what we have as it's written, okay? And the equilibrium is then what those values are at equilibrium. Now, some textbooks list this as an ICE table, initial change equilibrium. Some textbooks and some people that I've heard talk about this as a RICE table because this first line is always the reaction that you're looking at. I need that balanced equation to know what to do in the change, so I need to have it as the first row. And to emphasize that, they list it as a RICE table as opposed to an ICE table. Okay, so that's what this represents. Let's talk about this reaction right here. So we're talking about H2 plus I2 going to 2HI. Same reaction that we have here. Initially, I have 1 times 10 to the minus 3 molar H2, so that's right here, and 2 times 10 to the minus 3 molar I2, which is right here. Notice that this is done in Excel, so rather than times 10 to the negative 3, it's exponent negative 3. That's how that works in Excel. So that's why it says e to e negative 0.3. My change is always going to be, I'm going to take from the H2 and from the I2 to make 2HI. Now, it tells me that the concentration of HI after some time is 1.87 times 10 to the minus 3. So that's this value right here, okay? Notice that that means that 1.87 times 10 to the minus 3 is equal to 2x, and that's what I'm showing right here. Right? In order to find what the x value is, which I need to be able to do this concentration and this concentration, then I have to take and divide this by 2 to get 9.35 times 10 to the minus 4. Right? Now that I know that this is the x value, I can calculate this concentration. I say 2 times 10 to the minus 3 minus the 9.35 times 10 to the minus 4 gives me 1.065 times 10 to the minus 3. And the 1 times 10 to the minus 3 minus the 9.35 times 10 to the minus 4 gives me 6.5 times 10 to the minus 5. Okay, so that's how that works. Now that I have all of my equilibrium numbers, those concentrations, I can solve for the value of K. So this is a quotient that tells me the ratio of the reactants to the products, right? So if I put in the concentration of HI squared divided by the concentration of H2 and the concentration of I2, and I do that math, that'll give me a number that represents this particular equilibrium under these conditions. So the 1.87 is the concentration of HI. I have to square that to put it in here. We then divide by the 6.5 times 10 to the minus 5th and the 1.065 times 10 to the minus 3rd. That gives me 50.5. Okay, so that's what we're looking at in terms of that value. So that value we can then use to do other calculations for this particular reaction. Okay, since this one gave me one of the equilibrium concentrations, then I could find the other ones without doing things where I have to equal the K value. So I was able to calculate K here as opposed to what we'll do with other things. Now, let's talk about how that's going to work. And this thing up here, ignore it. Sorry, I meant to delete that, but it's not gone yet. Let's say we have a similar initial setup to what we did before. H2 plus I2 going to 2HI. Instead of calculating K, I want to find out what the concentrations of all species will be at equilibrium. So I start with the same type of table, but now I have a K value. I know what that K is. And we consider our changes just as we did before as x's, but I don't get this value here, or this value here, or this value here. That's what I want to solve for, is what's in here. I do that by setting this up in the K expression. So Kc is equal to Hi squared over H2 times I2. I know that Hi is going to be 2x, and I'm going to have to square that. And then the H2 is going to be 6.42 times 10 to the minus 5th minus x times 3.37 times 5 times 10 to the negative 5th minus x. So this is the expression that I have when I plug everything in. I can then start to simplify that by saying, okay, Kc is 50.5 because I calculated it on the last slide. And that's equal to this expression. I can then multiply these two out, right? That's what you see here is the multiplication of these two factors. And then I have to multiply that times the Kc, which is 50.5. And I move these over here to do that. So that means that 4x squared is now equal to this expression times 50.5. Distributing the 50.5, I get this expression, and that's equal to 4x squared. I move the 4x squared to the other side so that I then have an x squared, an x, and a constant, and then I can use the quadratic equation to solve for those to solve for x. All right. Quadratic equation, remember we do the b, which is the x value, the c, which is the constant, and the a, which is the x squared. We plug all of that in per this equation, and that'll give us two values, because we get one when we add the square root and one when we subtract the square root. The two values that I get when I do this math are 3.133 times 10 to the minus 5th molar, or 7.49 times 10 to the minus 5th molar. X has to be less than my starting conditions. And in order for that to be true, this cannot be used. So the value I have to work with is 3.133 times 10 to the minus 5th. That then becomes the x, and then hi is 2 times that to come here, right? So you end up with the values shown in the table above, okay? Does that make sense? I hope that makes sense. So we had to do all of that math. This is a quadratic equation. Most calculators can do the quadratic equation provided that you provide it with A, B, and C. So if your calculator can do that, it is not cheating to use that functionality to be able to solve those. Okay, so that's the deal there. Sorry, making myself a note. All right, let's talk about our next slide. Factors that can affect equilibrium. All right. So now I have equilibrium. It's been established. But if I make changes around that equilibrium, then that's going to change those values, which is going to put me into a Q situation, not a K situation. And then I have to figure out which direction I'm going to move to get back to equilibrium. We'll talk about this as the Châtlier's principle, which I'll show you on the next slide. But first, I want to talk about this in a way that is a little bit different. If I change concentration, right? Let's just say that I have this equilibrium and I add additional reactant to it. Now my Q has too much reactant, so it's smaller than K. That means I need to move in the forward direction to produce more product to make that work. So I'm moving forward to get back to equilibrium. If I add more product, then my Q is going to be larger than K, and I need to go backward to compensate for it. I can see changes in volume and pressure. Okay, those will only be a consideration when we talk about our gases, all right? So if I increase the pressure or decrease the volume, that pushes the equation toward the side of the reaction with the least number of atoms of gas, or the least number of moles of gas. So as we talked about it before, that N2O4 going to 2NO2, I have 1 mole of gas on the reaction side, 2 moles on the product side. So if I increase pressure or decrease the volume, that's going to shift forward. If I decrease the pressure or increase the volume, that's going to reverse it, and it's going to go backwards. Okay? Changes in temperature do 2 things. One, we'll talk about this later. All reactions either require heat to be put in to go, or they give off heat when they happen. So that means that heat is either a product or a reactant in those conditions. We can talk about it being a product, which is an exothermic reaction, or a reactant, which is an endothermic reaction. So if I change the temperature, then that's either going to add heat or take it away. And so I'm going to have to shift based on what kind of reaction this is, endothermic or exothermic, to deal with that. Now, the other thing that happens is that it changes the value of K. Once that temperature changes, I'm going to have a different ratio of product to reactant. It's not necessarily easy to predict how it's going to change, so we don't really talk about that, but it is going to change it. Now, I can add a catalyst. Catalyst is added to a reaction to drive that reaction, to make it happen faster. That's its purpose, is to make it happen faster. Since it doesn't matter how fast it happens, I always end up with the same ratio of product to reactant, there is no effect from the presence of the catalyst. So the catalyst does not matter. When we talk about Le Châtlier's principle, this is exactly what we were talking about before. So if I add substance to my reactant, they have to react to make more product. That's compared to my initial equilibrium, and that reestablishes the equilibrium with the same ratios, but different numbers. We talk about changing the pressure, and we talk about endothermic and exothermic, which is what we were talking about with temperature. So this is just a graphical representation of the things that I just talked about, okay? Let's talk about applications of Le Châtlier's principle. Let's talk about the reaction of N2 gas plus 3H2 gas going to 2NH3 gas. This is exothermic, meaning it gives off heat as a product. All right. So if I add N2, what's going to happen to that reaction? I add N2, which is a reactant. That means I'm going to have to shift forward to get back to equilibrium. If I remove H2, what happens? If I somehow take out that H2, that means that my H2 has gone down. I need to go backwards to reestablish equilibrium. If I put that into a smaller volume, what happens? Smaller volume means higher pressure. I need to go to the side of the reaction that has less moles of gas. I have 3 plus 1, 4 moles of gas here. I have 2 moles of gas here. So in a smaller volume, I'm going to shift forward to relieve that excess pressure. Right? If I increase the pressure, same thing. So smaller volume or increasing the pressure, both of those will drive it in that direction. Now, if you increase the temperature, what's going to happen? Well, two things. The value of K will change. That's going to happen no matter what. Since this gives off heat, that means it's going to make this want to go the other direction. So I'm adding heat, which is a product that's going to drive it back. And if I reduce the temperature, I've taken away heat, right? Then I have taken away my product, so I react forward to do this. And again, it still changes K. All right? Questions, comments, problems about any of that? Don't panic. Why am I saying don't panic? Because all of these things are going to seem extremely esoteric. We're asking you to remember a lot of stuff from the first half of this class. It's all very mathematical. This is a lot more calculations than we've ever done in chemistry before. You'll get used to it. As time goes on, this will become easier. It will make a lot more sense to you. But it's only going to make a lot more sense to you if you're doing these problems yourself. Okay, looking at them may help a little bit, but it's not going to help a lot to help you get to where you need to be to understand this material. So practice, 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 practice. And that will help you with those. The kinds of things that you saw today in terms of calculating concentrations, seeing where things go, that's going to be what we talk about for a very long time. Okay. When we talk about a lot of the other things that we're going to talk about, especially on the first unit test. So that's going to be a common thread that we'll talk about. So hopefully you don't have any questions. If you do, please let me know. Again, tell me what the topic was. Give me some idea what you're having issues with, what you don't understand, what you think it should be, whatever. And send that to me either via email or call me or come and see me. And I'll figure out a way to explain it to you. And if I can't do that via email or on the phone, then we'll set up a WebEx and talk about it, or you can come to my office and we'll talk. Okay? So hopefully that helps. That takes us to the end of our first lecture in 111, Chemical Equilibrium, and I will see you again when we start in lecture 2.